Vibration Analysis Rule 4, Amplitude Modulation and Sidebands, Understanding Signal Variation and Frequency Components. Introduction to Amplitude Modulation. Amplitude modulation in vibration analysis refers to a phenomenon where the amplitude of a vibration signal, the carrier frequency, varies periodically due to another influencing frequency, the modulating frequency. This interaction creates a distinctive pattern in the frequency spectrum known as sidebands, which appear symmetrically around the carrier frequency. The spacing of these sidebands corresponds to the modulating frequency. This concept is critical because it reveals mechanical conditions such as gear eccentricity, bearing defects, and other cyclic load variations. Unlike simple vibration signals, amplitude-modulated signals indicate that forces within the machine are not constant but fluctuate in a predictable manner. This fluctuation often results from mechanical imperfections, such as misaligned gears or localized bearing damage, which cause repetitive changes in load during rotation. Analysts rely on identifying these sidebands to diagnose faults accurately. The presence of sidebands, their spacing, and their amplitude provide clues about the severity and source of the modulation. For example, a gear with eccentricity will modulate the gear mesh frequency at the shaft rotation rate, producing sidebands spaced at one-order shaft speed. Similarly, a bearing defect will modulate its characteristic defect frequency as the component moves in and out of the load zone, creating sidebands at shaft speed intervals. Understanding amplitude modulation is essential for distinguishing between normal machine behavior and fault conditions, as well as for differentiating it from other phenomena like beating, which can superficially resemble modulation but lacks the structured sideband pattern. Let's see this pattern illustrates amplitude modulation in vibration analysis. In the time waveform on the left, we see a high-frequency vibration riding inside a slowly varying envelope, which indicates that the vibration amplitude is increasing and decreasing at a regular rate. This means the excitation force is not constant but is being influenced by another cyclic source, typically shaft rotation. When we look at the frequency spectrum on the right, this same behavior appears as a strong carrier frequency with symmetrical sidebands spaced evenly on both sides. The spacing of these sidebands corresponds to the modulating frequency, usually 1 times shaft speed. This structure is a key diagnostic feature and is commonly associated with conditions such as gear eccentricity, bearing defects, or cyclic load variations, allowing us to identify not just the presence of a fault but the mechanism causing it. Amplitude modulation in gears, gear mesh frequency and sidebands. In gear systems, amplitude modulation commonly occurs at the gear mesh frequency, GMF, which is calculated by multiplying the shaft speed by the number of gear teeth. The GMF serves as the carrier frequency, while modulation is introduced by variations in load caused by eccentric gears, misalignment, or gear tooth damage. These variations occur once per revolution of the shaft, meaning the modulating frequency is typically the shaft rotation speed, 1 order. As a result, the vibration spectrum displays sidebands around the GMF at intervals equal to the shaft speed. For example, if the GMF is 30 orders and the shaft rotates at 1 order, sidebands will appear at 29 orders and 31 orders, and possibly at 28 orders and 32 orders if the modulation is strong. These sidebands indicate that the gear teeth are not engaging uniformly, which can lead to increased wear and eventual failure if not corrected. The presence of multiple sidebands or sidebands around harmonics of GMF suggests severe modulation, often due to significant eccentricity or misalignment. Analysts use these patterns to pinpoint gear-related issues and assess their severity. Understanding this relationship between GMF and sidebands is crucial for diagnosing gear faults accurately and planning corrective actions before catastrophic failure occurs. Let's see this pattern is a classic example of gear-related amplitude modulation. In the time waveform on the left, the rapid oscillations represent the gear mesh frequency, while the slow rise and fall of the waveform envelope shows that the gear mesh vibration is being modulated once per shaft revolution. This tells us that the load on the gear teeth is not uniform and is changing cyclically, typically due to gear eccentricity, misalignment, or localized tooth damage. In the frequency spectrum on the right, this same behavior appears as a dominant peak at the gear mesh frequency, with symmetrical sidebands spaced at 1 times shaft speed on either side. These sidebands confirm modulation of the gear mesh signal and allow us to identify the rotating source of the disturbance. As the number and magnitude of sidebands increase, it indicates worsening gear condition and higher severity, making this pattern a key diagnostic indicator for early detection and trending of gear faults. Amplitude modulation in bearings, bearing defect frequencies and modulation. Bearing defects such as spalls on the inner or outer race introduce amplitude modulation into vibration signals. The characteristic defect frequencies, ball pass frequency outer race, BPFO, ball pass frequency inner race, BPFI, ball spin frequency, BSF, and fundamental train frequency, FTF, act as carrier frequencies. Modulation occurs because the defect moves in and out of the load zone as the shaft rotates, causing the impact severity to vary cyclically. This variation produces sidebands around the defect frequency at intervals equal to the shaft rotation speed, 1 order. For instance, an inner race defect will generate a strong BPFI peak accompanied by sidebands spaced at 1 order. These sidebands may also appear around harmonics of the defect frequency, indicating repetitive modulation. The presence of sidebands in bearing fault analysis is significant because it confirms that the defect is interacting dynamically with the load, which accelerates wherein increases the risk of failure. Analysts monitor these patterns to detect early-stage bearing faults and schedule maintenance before catastrophic damage occurs. Recognizing amplitude modulation in bearings is essential for accurate diagnosis and for differentiating it from other phenomena such as random noise or beating, which do not produce structured sideband patterns. Let's see this pattern shows amplitude modulation caused by a bearing inner race defect. In the time waveform on the left, the rapid oscillations represent the bearing defect impacts occurring at the ball pass frequency of the inner race, or BPFI, while the slow rise and fall of the waveform envelope indicates that the impact severity is changing once per shaft revolution. This happens because the defect moves in and out of the load zone as the shaft rotates, so the load on the defect is not constant. In the frequency spectrum on the right, this same behavior appears as a strong BPFI peak with symmetrical sidebands spaced at 1 time shaft speed on either side. These sidebands are a key diagnostic indicator because they confirm that the defect is dynamically interacting with the rotating load, distinguishing a true bearing fault from random noise or beating. As the sidebands increase in number and amplitude, it indicates increasing defect severity and accelerating bearing deterioration. Beating versus amplitude modulation, differences and diagnostic implications. Beating and amplitude modulation are distinct phenomena, though they can appear similar in the time waveform. Beating occurs when two frequencies that are close together interfere, causing the combined signal amplitude to rise and fall slowly over time. This results in a pulsating effect in the waveform but does not produce structured sidebands in the spectrum. In contrast, amplitude modulation involves one frequency, the carrier, being systematically varied by another, the modulating frequency, creating predictable sidebands around the carrier frequency in the spectrum. These sidebands are evenly spaced and repeatable, making them a reliable indicator of modulation. Diagnostically, beating often indicates two machines operating at nearly the same speed or slight speed variations within a single machine, whereas amplitude modulation points to mechanical conditions such as gear eccentricity or bearing defects. Analysts differentiate between the two by examining the spectrum. Modulation produces clear sideband patterns, while beating results in unstable peak amplitudes without consistent sideband spacing. Understanding this distinction is critical for accurate fault identification and for avoiding misinterpretation of vibration data.